I'm gonna start. Hi everyone, welcome to our DDLC seminar. Today we have Professor Ilya with Kolmanovsky as our invited speaker. So Professor received his PhD degree in aerospace engineering and also aerospace and Master of Science degree in 1993, PhD in 1995, and also Master of Arts degree in mathematics in 1995. They are all from University of Michigan, Ann Arbor. He is presently a periodic Carbon College professor of aerospace engineering at University of Michigan. Before joining the University of Michigan, he was with Ford Research and Advanced Engineering in Dearborn, Michigan for close to 15 years. He's a fellow of IEEE, IFAC, and U.S. National Academy of Inventors and has been elected as a member of U.S. National Academy of Engineering. He is presently serves as the editor-in-chief for IEEE transaction on control system technology. His current research interests are in control of systems with constraint and in control of aerospace and automotive systems. Let's welcome Professor.
Thank you very much for a very kind introduction. And I'm very pleased with this opportunity to be able to say a few words about recent adventures and not so recent adventures in supervisory reference governance schemes for safe control of uncertain systems and for model predictive control. What I'd like to do first is to tell you a bit about reference governors and more broadly some of my research in constraint control. So a lot of the things that I do have to do with worrying about state and control constraints and safety. And what distinguishes systems with constraints is that in addition to the usual objective of designing a controller that generates a control signal, here on the slide it's denoted by U of t, and you'd like to track reference commands, R of t, by suitably chosen output variables. Here they're denoted by Z of t. So Z of t has to be approximately equal to R of t. In constraint control, there are additional requirements on this or other variables of the system denoted by Y of t, that they have to belong to prescribed ranges. And these ranges are denoted by the set capital Y. And of course, such constraints could be safety or comfort limits, obstacle avoidance requirements, and actuator range and rate limits. Of course, constraints could be more complicated. For example, they could be time dependent in case of moving obstacles or be given by temporal logic statements. And so when working on constraint control, what we are trying to accomplish is to avoid the rollover for cars, trucks, and ships. We'd like to avoid compressor surge in aircraft engines, battery catching fire due to overheating, aircraft disintegrating during the flight due to excessive structural loads that could be induced by maneuvers or gust, or the onset of pilot-induced oscillations due to exceeding actuator range and rate limits. So we want to avoid situations like this. So how can constraint violation happen? Can happen in a number of different ways. But one specific situation I've been interested in is when you have commands issued to a nominal controller of the system by a human operator or a high-level planning algorithm. And these commands are unknown in advance. And if the nominal controller is not designed to handle constraints, these commands can be unsafe. And as the controller responds to them, the constraints could become violated. And so that's a situation that we'd like to try to prevent. Now, a basic tool to address the issue I just talked about is the notion of a safe set. And that's something that one of my mentors, Professor Elmer Gilbert at the University of Michigan, has introduced me many years ago, and we have collaborated on extending these ideas to systems with unmeasured set-bounded disturbances. Here they're denoted by W of t. Some of this research still continues to this day in my group. And a safe set, or what is more properly known as the maximum output admissible set, or infinity, is a set of all constant reference commands, R of t, as well as initial states x of 0, for which the ensuing output response doesn't violate the constraints for all times, and that happens despite unmeasured disturbances or uncertainties W. And in our work, we've been concerned about properties of these sets, such as invariance, how to compute and approximate them with suitable subsets, and also how to use them in applications. And one way to utilize safe sets to address the problem I just discussed is to use them for the implementation of what's known as a reference governor. The reference governor, the way to think about it, it's a safety filter that minimally modifies unsafe reference commands R of t that have a potential to induce constraint violation to safe commands V of t. To do that, what the reference governor needs to do is to maintain the pair consisting of the modified command and a state within a subset of the maximal output admissible set, and this subset is called P. There is particular reasons for why you use subsets. And at the same time, what you try to do is to minimize the difference between the modified command and the original command, because ideally you'd like the safety filter to be inactive and not do anything. And then the suboptimal implementations of the reference governor, such as a scalar reference governor, can be made computationally very fast and simple to implement. And in particular case of a scalar reference governor, the output of the reference governor, it's a linear interpolation between its previous output and the current reference command. And kappa here is the adjustable interpolating factor, bandwidth parameter. It takes values between 0 and 1, and you try to maximize it subject to this safety constraint. So this can be made very, very fast. Here's a cartoon on the left that illustrates the idea of reference governor. The reference governor here is shown as a character in the reference governor hat, and it modifies the reference command given by the captain, and this is shown by the user hat, and the command is then modified command is given to the PID controller to safely go around the iceberg and avoid the collisions and avoid violations of the constraints. Here's an experimental implementation of the reference governor, and this was done on electromagnetically actuated mass spring damper system. And the reference governor alters the abrupt step change in reference command, and it changes to a kind of this more gradual, smaller step and a more gradual change, if you can see here shown by the dashed line. And the effect of this is that you're able to satisfy the constraint on the overshoot of the position of the mass. So you essentially take out the overshoot by slightly adjusting the command by the reference governor. You know that you are getting older when there is an article appearing in IEEE Control Systems magazine written about your paper in a rubric 25 years ago. And it was, in this case, it was about the paper where the experimental results of the reference governor implementation for this electromagnetically actuated mass spring damper system I just talked about were reported. And of course, we've learned a few things about reference governors since that time. I'd like to summarize some of these ideas. The key ingredient in construction of the reference governor is this set P. And it turns out there is much flexibility how this safe subset can be chosen. In particular, it has to be a subset of or infinity of the maximal set, so that ensures that it is safe. but it does need to be invariant. So invariance is really not required for this safe subset. It has to satisfy a weaker property, what we call strong returnability. That is, if you start with a state inside this set and with a reference inside this set, and you apply the reference as a constant, then the trajectory of the system might leave this set, but there will be some future time instant t prime where the trajectory will pass through the interior of that set. Typically, we look for these subsets as zero sublevel sets of some continuous functions v tilde. And so there are multiple options how this set P can be constructed for linear models with linear constraints. This is very easy, reduces basically to linear programming for redundant, almost redundant inequality constraint elimination. If you happen to have a nonlinear system, but you know Lyapunov function, you could use sublevel sets of this function to define safe subsets. It's very amenable to machine learning in line with the topic of this seminar. If you happen to have a model of the system or a real system and you could simulate or experiment with it for different pairs of commands and states, you could develop a classifier to differentiate safe pairs from unsafe pairs, and such classifier, machine learning classifier, can be used to define this sublevel set P. And finally, you could avoid explicit construction of this set P altogether, and kind of like in model predictive control, use online prediction, basically implicit characterization based on online prediction to define the function v tilde and this subset P. Here's an example of a second order nonlinear system in continuous time, which can have a finite escape time. This is due to this x1 squared term here. And the controller is proportional integral type. There is also saturation on the control input. There is also a state constraint. And to implement the reference governor, what you can do is to simulate this system for different pairs of reference command and states. And blue points are unsafe or unstable, and then green points are safe and stable. And you could kind of fit a very simple classifier consisting of union of 4 boxes into this green area. This defines the function v tilde, as shown here on the slide. And that's enough to implement the reference governor. In particular, here we have this type of implementation working quite nicely and keeping the system away from not only violating the position constraint, but also satisfying input constraints and avoiding the finite escape time. And note that this set P is not invariant, so trajectories can leave it and come back to it, but the safety is still preserved. And in fact, not only the invariance of this safe subset P is not needed, but when searching for the modified reference V, which should be as close as possible to our original command R of t, the exact solution of the optimization problem is not required. And any value V prime, which satisfies an easy to check acceptance criterion, can be used. And so by exploiting simplified sets P, as well as inexact solutions to the optimization problem, one is able to obtain very simple implementations from the perspective of chronometric loading and ROM size that keep the system safe. And also through this mechanism, reference governors can handle uncertainty in availability of the computational resources if that becomes an issue. So if you'd like to know a bit more about some of these approaches, my colleagues and I have written a couple of survey articles on reference governors, and they discuss underlying theory, over 20 extensions of the basic reference governor scheme I spoke about, and many applications in different domains. And this work is really by multiple groups worldwide and multiple researchers who worked on these topics. I just wanted to mention very briefly a couple of recent applications of reference governors that we looked at not so long ago, and one of them is for vehicle lane keeping. So what you're trying to do is to keep the vehicle within the lane boundaries, as it might perform some kind of a lateral maneuvers. And the idea here is to apply the reference governor to modify a lateral command for the vehicle where it wants to be in a lane. In this particular case, we worked with the kinematic model. This was a low-speed scenario. At higher speeds, you would use dynamic model. And the nominal controller here was based on Control Lyapunov functions. And you see here there's some sub-level sets of the Control Lyapunov function that are scaled to be safe, and they change as you adjust the reference. You're trying to maintain the vehicle in this dashed polyhedron on lateral position and yaw angle plane. And so pretty much you can command different lateral positions to the vehicle, and the reference governor will modify the command, and keep the vehicle within the lane boundaries. These are some simulation results that we've done on curvy roads, as well as real vehicle experiments with a vehicle that looks like this, where we essentially go through a set of lateral maneuvers, for example, to avoid some kind of an obstacle, a pothole perhaps, on the road, and make sure that we don't that this vehicle doesn't stick out outside of lane boundaries. So that was an interesting application. And just to show briefly another application, we've looked at the use of these ideas in spacecraft applications, in particular for spacecraft rendezvous and docking maneuvers. And one way to implement the reference governor in these applications is to have it output a virtual position of the chief spacecraft to which you are trying to dock. So instead of commanding the deputy spacecraft to approach the chief spacecraft, you command it to approach a virtual chief spacecraft, and then the reference governor gradually brings the chief spacecraft, this virtual chief spacecraft, to the real chief spacecraft. And how to generate the position of the virtual chief spacecraft? Well, one way to do it is to look at the trajectory of the orbit of the chief spacecraft and time shift it. And so for that reason, this reference governor is called time shift governor, because we command the time shifted position of the chief and then gradually eliminate this time shift from the system. And you can see the maneuvers are quite interesting. What we are trying to do here is to make sure that the spacecraft stays within line of sight con constraint of the chief spacecraft. And this pink point shows the position, the commanded position, so the position of the virtual chief spacecraft. Sometimes it actually moves backward because the real chief accelerates along its nominal orbit. This is in cislunar space near the moon. In the perilunar region, velocities tend to increase. Okay, so hopefully this is an introduction to reference governors. And one of the recent areas of interest in my group was how to develop reference governors for systems which not only have large uncertainty in dynamics, which have large uncertainties, and this uncertainty could come in dynamics, in operating environment, in constraints, and even in available computational resources. But also, I've been interested in cases where characterization of this uncertainty is poor, and what I would call less specific than in traditional robust and stochastic constraint control. And we think that such reference governors can play a role in achieving resilient autonomy, in particular for aerospace applications. And so how one can approach some of these systems with large uncertainty, and clearly closer integration of constraint control and adaptive control can play a role in addressing such problems. And recently with Professor Pen Zhao and Naira Havikian, we looked at integration of reference governors with L1 adaptive control. And the basic idea is that the L1 adaptive control compensates for the uncertainty so that from the perspective of reference governor, the system the reference governor has to deal with behaves or matches the prescribed nominal model. So reference governor really doesn't know much about uncertainty because the adaptive controller compensates for it. Of course, there has to be some constraint tightening to account for the impact of the uncertainty, because obviously the compensation is not perfect, but this pretty much can be done. And this approach leads to promising results. For example, the ability to fly around and land on an asteroid, essentially without much knowledge of the gravitational field. The animation here shows the results for the case of model predictive control, but similar results can be obtained also for the reference governor. Now, here's another approach, how we can integrate learning into reference governor. So suppose we have a system that underwent a change. For example, we had a truck, and that truck has been loaded, so its center of gravity has changed. Maybe we had an aircraft and a portion of the wing of the aircraft has fallen off, more extreme scenario. And let's suppose that somehow the system is stable with the nominal controller, but we are not sure which commands are safe and which can cause constraint violation. So what can we do in such case? What we can do is to take the system to the side and experiment with the system, applying different piecewise constant command profiles. We can see how the system responds, and we can try to estimate from those data a safe subset P that we need for the implementation of the reference governor. And the idea would be that as learning proceeds, the conservatism in limiting the reference command will be reduced as the reference governor gains more knowledge about the system response. And of course, we are interested in ensuring anytime safety with such approaches, both during learning phase and once learning has been completed. Now, how to actually design and how to implement such a safety critical reference governor? Well, what one can do is to define a capital DI function, and that function has actually a very simple definition. It's a peak. So if we have constraints that are described by some nonlinear inequalities, hi of x and v less than equal than 0, what we can look at is a response of the ice constraint output to a step input. And we can look at the peak deviation in that response from the steady state value in the direction of the constraint violation. So the formal mathematical definition is given here. And z here, it's a pair consisting of initial state at which we start the trajectory, as well as the constant input command that we apply to our system. So this is a function, the peak function, what we call. And you need to know something about this peak function. Clearly, if you know nothing about the system, this problem is hopeless. And so what we'd like to have some kind of a bound on that peak function. The bound is denoted by this phi sub I. Perhaps this could be, might know, a Lipschitz constant. If our system has linear constraints are linear, then you could show that this peak function is in fact Lipschitz. For nonlinear systems with more general constraints, this phi function can be something more general, I suppose. But if you have that bound and you happen to know it a priori, that bound, you can combine this bound together with measurements of the peak. So once you apply the steps and you collect measurements, you have a data set. And so you can build an upper bound on this peak function, which we denote di bar. And essentially, it's defined in straightforward way from measurements and a priori bound that we know. And then the safe subset that we can use for reference governor implementation is pretty much defined as a sublevel set using this di bar function. As shown in the slide, we have to do a bit of a steady state constraint tightening. I should point out that we do need to assume here that the system is stable to be able to apply these ideas. And the other aspect is that we have to account for the noise in measurements of the peak. And this is simply because for second-order system, you can predict where the peak location is going to be. But for higher-order systems, for nonlinear systems, it's much easier to predict the settling time than know where the peak location is going to be. And so for that reason, we can sort of measure the peak up to some tolerance, but not exactly. Here's a safety critical learning reference governor developed using these ideas, and we apply it to spacecraft docking maneuvers. And here, as learning proceeds, the maneuver is becoming more aggressive and shorter in time duration. So as we learn more, the maneuver lasts less time, and it approaches closer to the constraint boundary. Here they're shown by this dashed red lines. This is a line of sight cone constraint that we worry about. And that's the type of behavior you'd like to see. Here's another example where we apply learning reference governor to rollover avoidance, and this is done for a truck. And this truck has been loaded or modified in some way in the field, so the center of gravity has changed. And if such a truck proceeds on the mission without reference governor, it could roll over. And so what we can do in that situation is to let the learning reference governor modify the steering angle and enforce the constraint on load transfer ratio to be able to prevent the rollover. And so before learning, when we just operate with a priori bounds that are very conservative, reference governor is very conservative, and as a result, the vehicle is not able to follow the desired maneuver during the mission. What we can do is to take this vehicle to the side and experiment a bit, applying different steering commands to that. And then after we learn for a while, now we are able to do significantly more aggressive maneuvers, and in fact able to complete our original mission and do the maneuver safely without violating the constraints. Won't talk about details, but you can make this scenario a little bit more challenging, assuming that you have a vehicle in which you have a fuel slosh. Dynamics are more complicated, but through learning, you could also enforce the constraints on load transfer ratio and prevent such truck from rolling over. Now, one of the limitations of the learning reference governor, as I have just described, is relatively slow learning. And you could see that it takes multiple experiments to collect enough data to characterize a subset P that we need. And so more recently, we've looked at ways of addressing this. Conventionally, what we've done was to collect, when collecting the data set, was that for each step that we apply to the system, we record the state at the beginning of the step, x of t, then we record the reference v of t, and then the peak di. And so one step would yield basically one data point. But of course, all states, as you kind of move along the trajectory before the peak occurs, they're going to have the same peak. And so, in fact, from a single trajectory, you can easily collect multiple state reference command and peak triples. And so a single step yields, in fact, multiple data points. And this is what we call enhanced data collection. And in fact, now we collect all the data from using this idea. The data set grows quite large, but we can apply data pruning algorithms to essentially eliminate some of the data points and keep it to the memory size that we have available. And so here's an example of a spacecraft with flexible appendage, where as you command reorientation to the spacecraft, you want to keep the orientation appendage deflections and control input within the prescribed limits. And if you compare learning reference governor based on conventional data collection with learning reference governor based on enhanced data collection, I've just described, as well as reference governor based on exact model. So this is green, standard data collection is blue, and then orange is enhanced data collection. What you observe is that the orange becomes closer to green much sooner. And so this reflects the fact that with enhanced data collection, you are indeed learning much faster to be able to perform range of these maneuvers. Another recent extension is to the case where this learning reference governor only uses output measurements rather than full state. And this extension is, of course, important if one wishes to apply learning reference governor directly to black box systems where you don't know what the states are, but you can take certain sensor measurements and measure some outputs. And the trick is to use the delayed values of the output as a surrogate for the state vector, and then you can essentially proceed with the rest of the construction using this trick. And the details are in the paper that I've just shown. Now, another opportunity is to optimize the sequence of steps applied to the system. So the actual sequence of step responses that we go through. And this is an experiment planning problem. And there is different techniques you can employ. It's interesting that we look back 25 years ago and found a paper that we wrote back then on set membership experiment planning for Lipschitz models. And we think that this learning reference governor setting nicely fits into this framework. And some of our initial simulation results seem to be quite promising in terms of designing exactly the sequence of steps we have to go through to learn faster. This is safety critical learning reference governor I spoke about. I wanted to briefly mention a non-safety critical version of learning reference governor as well. It operates a bit differently. It starts with no or little command limiting, and then it tightens a safe set in response to constraint violations during learning. And so this is a different learning reference governor because it does violate constraints during learning. In fact, it learns from constraint violation. It's not going to be safe during the learning phase, but hopefully after the learning is completed, it's safe or close to being safe. Interestingly enough, in this case, constraints may not be known a priori. We only need to know if they are violated or not. Just very briefly to show one example. These are truck simulations, I believe. And what we are trying to do is to have the vehicle learn not to roll over with this non-safety critical learning reference governor. What happens is that each time the constraint violation happens on low transfer ratio, we tighten the safe set description. Essentially, we reduce this gamma of V. And there is a specific way we do it so that after multiple learning iterations, indeed, we are able to avoid rollover. Now, of course, in practice, if you use such an approach, you have to make sure that constraints violations are not catastrophic. For example, if you consider real vehicle application, you might add some kind of sidebars to the vehicle to ensure that the actual rollover doesn't happen. Undo this type of non-safety critical LRG, deploy it or have it learn in virtual world rather than the actual physical world. We've actually tested such schemes experimentally, and this was joint work with Professor Anna Stefanopoulou at Michigan and our students. And in that case, we had a non-safety critical version of learning reference governor on a running gasoline engine. And this was a high exhaust gas recirculation rate engine. And this were essential, these high rates were essential to be able to reduce oxides of nitrogen emissions. And here, learning reference governor learns to slow down throttle closure in such a way as to leave enough air in intake of the engine for combustion, acceptable combustion to take place, and essentially avoid engine misfires. So that was an interesting experimental application. I would like now to shift the topic or the discussion a little bit and talk about what I would call constrained learning. So traditionally, when we deal with uncertain systems, we assume that dynamics or environment are known, but constraints themselves are specified. They're given to us by some known functions, by some known limits. Turns out that that's not quite true in applications, as in some applications, constraints themselves are not a priori characterized, at least in terms of functionally. And so these constraints also have to be learned. And we've encountered such a situation also about 25 years ago when working on stratified charged combustion engines, where the fuel is directly injected in the combustion chamber and sort of have to swirl around and reach the location of the spark exactly at the right moment for acceptable combustion to proceed. And so there is an intricate relation between injection timing when you inject fuel and spark timing when you actually start the flame, so to speak. So there's constraints, and these constraints, in fact, are dependent on air-fuel ratio of the engine, exhaust gas recirculation, EGR rate, rail pressure. And so it's actually quite a complex function. And at that time, we looked at support vector machine learning to determine the constraint boundaries from pretty much data. And obtain a functional description of those constraints. And turns out that we came back to the same kind of issues more recently, realizing that even if you take a simple two-link robotic manipulator and you throw a couple of obstacles in a workspace, if you look at configuration variables, which are joint angles of this robot, the collision-free space actually has quite complex geometry, and you could kind of tell that constraints actually are quite complicated and not that as easy to actually specify in general. And so what you can do is to throw a few points here and sample, see whether these points lie in collision-free space or parts of the space where you have collisions, and train support vector machine classifiers to provide functional description of the constraints that you can then use for constraint control, for example, in model predictive control and in reference governor design as well. Now, what's very interesting that we found that for a number of kernels in support vector machines, in particular Gaussian RBF kernel, the MPC problem that you end up with reduces to what we call what's known in the literature as difference of convex DC programming problem, for which there are tailored solvers. So it's a known class of optimization problems for which tailored and computationally efficient solvers exist. And so with that, you're able to solve MPC problems and perform various maneuvers with this manipulator, where you sort of have to move it, for example, from the stretch position to more position like that, while avoiding obstacle hits and so on and so forth. So there's some interesting applications where you want to learn the constraints offline. Now, the other class of situations where constraints are not known is, and you need to do online constraint learning, is, for example, you might have a robot that enters an area, perhaps a room where the walls are not known precisely, they have not been a priori characterized. Perhaps you have some kind of functional description of them, parameterized by a few parameters. And so what you try to do is to operate safely within that area, within that room, while relying on measurements of the constraints to try to identify what the parameters in the constraint descriptions are. And you need to know some a priori bounds on where the parameters can be. And then in terms of identification of the constraints, there's really one type of approach you can use is a set membership-based experiment planning, because you want to plan your position within this room safely, but also optimally to enhance the data collection and try to reduce the uncertainty in the parameter set that you're trying to identify. And so then the reference governor at each epoch ensures that whatever reference you command is safe with respect to the your current estimate of the plausible parameter set. But as learning progresses, your size of this theta sub k, the set of plausible parameters, reduces, and therefore the set of feasible reference commands that you can follow expands. And so initially you could be very conservative in terms of which maneuvers you can perform, and then once you proceed with learning, you can become significantly more aggressive and explore more space in this case. If I have a few more minutes, I'd like to tell you a little bit also about the model predictive control, some of the model predictive control research going on in my group, so this moving away from reference governors and thinking about perhaps more general schemes for dealing with constraints. And just as a reminder, in MPC, we tend to solve an optimization problem. And it's typically a trajectory optimization problem subject to constraints. And we use the first element of the optimal control sequence for control, and then we recompute the solution. Now, of course, one of the key challenges or Achilles heels of MPC is the computations that are heavy. And so you realize that if you try to implement MPC controllers on, for example, board of quadcopters or small aerial vehicles. And so we've been trying to think of ways how to augment reference governor type schemes to model predictive controllers in such a way as to have computationally simple and safe and effective solutions. And so a couple of ideas we came up with. One is what we call multi-fidelity reference governor MPC scheme. And the idea here is that MPC and reference governors, they use different fidelity models. So MPC uses low-order disturbance-free, typically linear model, and it only enforces input constraints. So the trajectory optimization problem that MPC solves then is very simple. On the other hand, the reference governor uses high-fidelity, nonlinear model. It also uses disturbance bounds for uncertainty, for disturbances. And it predicts trajectories and decides on modified reference safety. It also enforces state constraints. So MPC does simple optimization, and essentially reference governor validates the trajectories generated by MPC and decides if it can advance to them or not. So that's the setting that we've studied. And some of the theoretical details are in some of our papers. But here is an example where we're trying to dock to a rotating spacecraft. And here the MPC uses low-order model with 12 states that linearized, and reference governor is able to use a high-fidelity model with 12 states that accounts for rotational dynamics in addition to translational dynamics, and that model is nonlinear. Now, another idea that we looked at is what we call computational governor. The way that idea came about is looking at cases or situations where the MPC solver, the optimizer, needs a lot of iterations to converge. Now, if the system you're trying to control with model predictive controller is close to steady state, and you use the warm starting, then the MPC solution from the previous iteration is not so different from the optimal solution. And typically, one iteration per time step is sufficient for convergence. The spike in the number of iterations, and you see it here on the plot, occurs when the problem data change. For example, when there is a drastic change in the reference command R for Y. And so this is where we have a spike in the number of iterations. So then the idea is pretty clear. What you can do is that instead of applying this pink step, is to use some form of reference governor to replace it by smaller step and perhaps a ramp. And if you do it in exactly right way, maybe you could achieve convergence of the optimizer within one iteration. And so that's precisely the idea of computational governor that minimally alters the reference command to enable MPC optimization problem to be solved cheaply, efficiently, and reliably to completion. I don't think I have time to go through the details of this construction. I'll just simply mention that this reference governor, so the computational governor is the scalar reference governor, but the constraint it enforces, that constraint exists not in the physical domain, but within the optimization algorithm. There's a Newton step that the interior point method that we use to solve the underlying quadratic programming problem. That Newton step, we are trying to limit it to a value of 1 in terms of infinity norm. And then nice things happen that are further discussed in our paper. And with this approach, we are able to have basically to keep the solver happy, and it's able to find reliable solutions with one iteration. These are some of the experimental results on inverted pendulum on a cart in a lab, and be able to sort of control the system with one iteration per time step that you see here on the screen. The number of iterations always stays equal to 1. Turns out that the solution inspired by this our computational governor has been actually implemented by Toyota Motor Corporation in production. I'll skip that. And I'll just mention that the development of other governance supervisory schemes for model predictive control represents a nice opportunity for continuing research. And we've been pursuing several extensions of these ideas that, again, I'd be happy to speak more offline if there is interest. I spoke about learning reference governor. We look at a couple of other schemes and approaches for ensuring safety with for reinforcement learning controller, as well as with controllers that are based on machine learning type perception. Again, in the interest of time, I'll skip that. And this is my last slide. Just to summarize some of the discussion and a few closing thoughts. So reference governors that I talked about, these are add-on safety filters. They apply to reference command to enforce state and control safety constraints. Hopefully, as I've convinced you, learning can be integrated into reference governor design to handle unknown but stable system dynamics without relying on overly specific or restrictive assumptions on the uncertainty model. Practical constraints can be complex, and if a priori unknown, they may need to be modeled from data using machine learning techniques, or they may have to be learned online. And then finally, supervisory schemes for MPC can be developed that improve reliability of MPC with short horizon, reducing computational time, and expanding the closed-loop region of attraction. And some of the ongoing research is to integrate learning into such supervisory schemes that are intended for integration with MPC controllers as well. And that completes my talk.
Thank you, Professor. Let's just wait a bit of minutes for the audience to post the questions, because we have a bit delay, like from the Zoom and also YouTube Live. So actually, I have one question. Like for the learning, like we have to explore a bit to get the data for the data collection. I just wondering, like any strategy like to guide it, like how do you get the data? Like for the action space, we have different direction. Any strategy can guide like this collecting process?
Yes, so obviously the setting we are looking at is very specific to reference governors. And so as we decide on experiments, typically we decide on a sequence of steps to apply. And so optimization of that sequence of steps, or even deciding on the next step to apply to the system, it's an experiment planning problem. And so in the literature, there are different experiment planning procedures. In particular, and often you assume some kind of linear parameters, regression model, maybe quadratic model in terms of classical design of experiments. But there are a set of methods that work directly with Lipschitz models. That is, you assume that your model can be anything subject to, say, a known Lipschitz constant. And so you could essentially plan the experiment. And the idea is always the same. You try to position the location where the measurement is taken to maximally reduce the uncertainty, right? To maximally shrink the set of possibilities. So essentially that's one procedure that we have tried. That is, we have essentially looking at all possible steps that we can apply, and we have a planning score, and this planning score is linked how much this basically the volume of the set of feasible models shrinks, and we try to maximize the shrinkage pretty much. So that's one process. Now, of course, there are other procedures that you can think of that would be based on different assumptions, but yes, that is an important problem, how to optimally collect data and speed up learning. Yes, so that's a process that we've looked at.
Thank you, Professor. We have one question. It's hi, Professor. Is it possible to generalize the results to distributed scenarios? In particular, there exists couple constraints, but each agent only knows its local state as well as the states of its neighbors.
Mm-hmm. Yeah, this is an excellent question. In other words, is it possible to extend some of the ideas to the multi-agent setting, perhaps even game theoretic setting? We haven't done it, but there may be possibilities. There may be possibilities to do that. Generally, there has been work by not by our group, but by other groups. Actually, by our group as well, on the distributed reference governors, where individual agents they follow the reference commands, and these reference commands are modified by the reference governor, and you try to avoid safety constraint violations. And this type of schemes can be designed under different assumptions, but as far as I know, learning hasn't been yet integrated into this type of scheme. So that's an excellent question. I'm not aware that this has been done, so it's an excellent topic for future research.
Okay. There's another question. Thanks for the talk, Professor. I wonder how the transient behavior of the dynamic system can be enforced for constraint satisfaction using the reference governor.
I'm sorry, could you repeat the question?
Yes. I wonder how the transient behavior of the dynamic system can be enforced for constraint satisfaction using the reference governor.
I see. Well, so in terms of the transient, so first of all, we are enforcing constraints during transients, right? That's the whole point. It's not just steady state, but it is during the transients. So effectively, what we are doing, we slow down aggressiveness of those transients to ensure that the constraints are satisfied. And the specific approach that how this transient is slowed down is that we always make sure that the command that's being applied at any at any time instant and the state, they are consistent, so they're not too far apart to cause constraint violations, roughly speaking. So yes, absolutely, we do handle, the whole game here is to handle constraints during transients, and these schemes, they do enforce constraints during arbitrary transients on the assumptions on the initial condition. If you'd like to have convergence results, for example, you'd like to ensure that the modified reference command converges to the original reference command, that of course requires extra assumptions. So for example, such results can be obtained if the original reference command is a constant in time or becomes constant eventually, or it's small varying around a constant value, or it's slowly varying. So it's some kind of ramps that slowly varying. Under those conditions, you may be able to show with the right additional assumptions that you're going to converge in finite time. So V of t becomes equal to R of t in finite time.
Thank you, Professor. There is another question saying, dear Professor, could you please explain the relationship between the forward invariance property and the concept of returnability?
Yes, absolutely. So in terms of forward invariance, the idea is that if we start with a state in a set, then the trajectory stays within that set for all future times, right? So this is forward invariance or a positive invariance property. Now, if the set is strongly returnable, a trajectory can leave this set. It is allowed to leave, so the set is not required to be invariant, but it has to satisfy the property that at some future time instant, the trajectory comes back to the set and passes through the interior. So returnable means it comes back to the set, but then strong means actually comes back to the interior. Now, after that time instant, it could leave the set again. But that's a strong returnability property. And that time instant, where the trajectory passes through the interior, it doesn't need to be known a priori, and it doesn't need to be necessarily a function of it doesn't need to be the same for all states in the set. So it could be different depending on where you start in the set.
Yeah, we have one last question. It's, Professor, have you compared the performance of reference governors with that of adaptive or stochastic control barrier function for reference tracking?
I would say that in terms of stochastic setting, there are variants of the reference governor, so-called stochastic reference governor, that have been developed, for example, to enforce chance constraints. And so the challenge in stochastic formulations of the reference governor is that and this is generally the case in model predictive control with say additive disturbances, let's just say that don't have a compact support, is that you could lose feasibility. And the same thing happens with stochastic reference governor, that if you wait long enough, there will be a point that the feasibility will be lost. So then the key point is that you need to build in some kind of infeasibility handling mechanism. And that's very simple. In the reference governor case, you just hold the previous reference command constant. But then you have to be able to show that with that infeasibility handling mechanism, your design intent, say chance constraint, actually do hold, right? Because now the system has been modified. That can be done under certain assumptions, but those assumptions are a bit tricky. So there is an extension of reference governor to stochastic world. And then to answer the second question, have we compared sort of stochastic variance of reference governor with adaptive stochastic control barrier functions? I think the answer is not. My general feel is that there are a lot of synergies combining reference governors with control barrier function solutions. We looked at some of the synergies and recently actually submitted a manuscript describing sort of complementary features of those methods. That they're not necessarily competing, and there are actually some synergies, and you could similar how you can use reference governance to enhance model predictive controllers, you can use reference governance to enhance control barrier function solutions. So we definitely see that there is a synergy. This work was in very deterministic setting, in a sense that we haven't looked at stochastic setting. So I can't give maybe a full answer to that question, but perhaps perhaps these are some thoughts that could be useful.
Okay, thank you, Professor. I think that's all for today's seminar, and thank you so much again for accepting our invitation, and we really enjoy your talk.
Thank you so much for the invitation. It was a pleasure to be here.
Bye-bye.